Before we get going, anybody have any questions about anything? All right, so I put a new module on Canvas. Basically, underneath the place where I post all my YouTube links, there's a new module called Quiz Solutions. I just remembered that I forgot to post the solution to the first quiz, so that one's on there now. If you have any questions about either where you went wrong on that quiz, or if you just want to see how I did them, I will post the solution to quiz 2 sometime by the end of the week. But yeah, I'll try to have those graded sometime today or tomorrow. Do we know what's due tonight? Okay, so I think section 2.1 is due tonight, and the quiz is due sometime before we all leave today. What else? And the first test is on Wednesday. I'm going to send out a survey sometime tonight. I would like to have I would like to offer an expert review session or two between here and next Wednesday. So I'm going to try to figure out what times work well for y'all. So keep an eye out for that in your email sometime today. All right, so we're in the middle of section 2.2, talking about the derivative as a function. Real quick, and this is kind of a relationship between differentiability and continuity. If I have a function f that is differentiable at some point a, then it has to be continuous there too. So you can think of it in a way, differentiability supersedes continuity. And another idea you can pull out of this is something called a contrapositive. Let's say this is true. If f is not continuous at x equals a, then f is not differentiable. So your function has to be continuous for it to even have a chance of being differentiable at a point. And we saw you might have one without the other. So I think the last example we looked at on Friday was the absolute value function. The absolute value function is continuous everywhere, but we did find a place where it's not differentiable. Its derivative doesn't exist. Any questions there? All right, I want to go through a couple more examples of when we kind of hinted a little bit about higher order derivatives. So we can find a derivative, but since that derivative is in itself a function, we can find a derivative again and again and again with many functions. So it was a long time ago now, but the first function we looked at, or one of the first functions we looked at on Friday, was this f of x equals x cubed minus x. And just to refresh your memory, we found out that this was true. The derivative of that function, f prime, is equal to 3x squared minus 1. So now I'm asking for this new function called f double prime. So the first derivative of f of x is this f prime function. If I want to find the second derivative, that's equivalent to me finding the first derivative of the first derivative. Now I want to find essentially the first derivative of 3x squared minus 1 with respect to x. So remind me, how do we do things like that? What's the thing called? Yeah. What is that thing called? DQ. There you go. So yeah, we're looking for, and I should really be explicit, f double prime of x. And this is going to look a little different than what you're used to, but let's talk about the parallels. Give me the limit as h approaches 0 of f prime of x plus h minus f prime of x all over h. So I'm trying to find the second derivative which means that parent function, the function I'm trying to find that limit with respect to, is no longer f, it's f prime. I'm trying to find the derivative of f prime. I got the limit as h approaches 0 of 3 times x plus h squared minus 1 minus 3x squared minus 1 over h. I expand this bracket, I get 3x squared plus 6xh plus 3h squared minus 1 minus 3x squared plus 1. So what cancels? 3x squareds cancel. Positive 1, negative 1 annihilate each other. And then what's left is I have an h term that I can factor out of the numerator and denominator. So what I have now is this, the limit as h approaches 0 of 6x plus 3h, which is equal to 6x. Let me pause there. I went through that pretty quickly, and it's got a few days off. Any questions about how I got to that second derivative of 6x? So f prime of x is equal to 6x. I am going to leave this one for you. So I'm going to tell you the third derivative of this function. So if I were to run through this process again to find the third derivative, I would get a constant of 6. We've done a lot of these different quotients. Assuming y'all did the quiz, I'm sure you got a lot more practice with there. Yeah, I'll go ahead and skip that one. Any questions about how we got 6x and 6, though? Or about how we got 6x? Go ahead. No term. Made this mistake up here. If you don't distribute that negative sign properly, you're going to wind up with a limit that you can't evaluate. All right. So the last thing I want to show you here is just kind of how all these things are related. We talked about it quite a bit on Friday, but I think now that we have a concrete example, let's take a look at it. So this red curve here, this is f prime of x, 3x squared minus 1. And this right here is what we just found, f double prime of x, which is equal to 6x. So a couple things to note here. This parabola, where is this parabola going to have a derivative of 0? What x value is that going to happen? 0, right? So does the blue line, that second derivative, does that make sense? So, yeah, the second derivative is equal to 0 at x equals 0. Does the fact that the slopes of this line, f double prime, does it make sense that this function has positive values when x is positive? Similarly, when it's negative, that's because my parabola is decreasing. So that's how the second derivative is related to the first, which is also the same relationship between the third derivative and the second. So this one right here is your second derivative. F double prime of x is equal to 6x. And this right here is f triple prime of x is equal to 6. So one of the ways we characterize the derivative is it is the slope of the tangent line. But what kind of function is f double prime? Like what did I graph there? It's a straight line, right? So what can you say about the slope of the straight line? Yeah, it's the same everywhere, which is why my derivative of that is just the number 6. It's just equal to its slope all the time. There would be. So let's talk about it. What if I wanted to do, and kind of a weird notation here, as long as I can write it, f in parentheses, Roman numeral x. So one of the ways we just, this is a great question. We just said that, the derivative, if you're looking at a graph, the derivative of the graph of the function is equal to the slope of that graph at any point, right? Look at that line, y equals 6. What does it slope? Anywhere. So we're saying the slope, we're saying the fourth derivative is 0. Does that make sense? Okay. That is true. We'll talk about why we can say that's true in just a bit, but yeah, the derivative of the fourth derivative is going to be 0, and really any derivative after that is 0 for a similar reason.
Would all derivatives eventually be 0?
No. Of this function, yes, they do, but not of all. We'll see some examples of that. In fact, if you think back, I've heard a lot. I heard a lot of talk about what I assumed was the second question on the quiz in here when I walked in. You could take an infinite number of derivatives of that, and you would never reach it. But you could keep finding new ones. Any more questions about this guy here? Right. So that was 2-2. So now we're going to get into some formulas. Basically, a lot of you have said use the phrase power rule, which you probably suspected that was coming sometime soon. So let's get into a few of those now. And let's just do a kind of a recap on what derivatives mean to us. So if I ask you about the derivative of a function, what does the derivative tell us about a function? So anything you got, just go ahead and shout them out. Slope of a tangent line. Awesome. Back up. Slope of a tangent line at a point. Anything else? Yeah, I can tell us that. Tells us where a function is continuous. I mean, that's one of the things we just talked about. If the derivative exists, then function has to be continuous there. Anything else the derivative tells us? Even an abbreviation here for something I've used in the past, something you may have seen. The instantaneous rate of change, which really is, when you're talking the slope of a tangent line, that is what you're looking for. You're trying to find out, what that slope is, what that rate of change. If I can get to that limiting situation where I'm only looking at one point. So up to now, how have we found all the derivatives that I've asked you to find? Difference quotient. And really, that's where all derivatives come from. But we can use that difference quotient to help us take some shortcuts. So one thing I'm going to show you here, and this very much related to the question that Cameron just asked. I want to find the derivative of some constant. What's the derivative of x equals k? So let's use the difference quotient as a means to, develop this formula that we can just rely on. So I have the limit as h approaches 0 of f of x plus h minus f of x all over h. Sorry? Oh, sorry. This is equal to f prime of x. What is f of x plus h in this case? It's okay, right? And f of x is? Okay. So this is pretty simple. So I get the limit as h approaches 0 of 0, which is 0. So if one of the ways we think about derivatives is the rate of change of a function, what can you say about the rate of change of a function that is a constant? Yeah, it never changes. So its rate of change better be 0. So, as we build these things up, we're kind of trying to bypass that difference quotient. Now, if you see a constant, I ask for a derivative of it, we know that it vanishes. The derivative becomes 0. Any questions there? All right, and the power rule. So I want to find the derivative of this thing, this function, x to the power of n, where n is a positive integer. So, and n could be any positive integer. So let's start working on that. It'd be really great if we didn't have to do that difference quotient every time for this. So hopefully our last time doing it for this kind of function. By the limit of h approaches 0 of f of x plus h minus f of x all over h. F of x plus h is going to be x plus h to the power of n. F of x is going to be x to the power of n all over h. And here's the weird part. What happens with x plus h to the power of n? Can I simplify that? So I think we know how to like FOIL that out if it's the power is 2, but like what if it's 100 or something? One thing I'm going to guess, I'm not going to call anybody out, but I'm going to guess that at least somebody might have been tempted to say this is true. So can't quite shortcut it that much, but some of you may have seen the binomial expansion theorem or Pascal's triangle to deal with things like this in the past, but I'll generalize it for you. So expanding that x plus h to the n, you are going to have those bookend terms of x to the n, then you have plus n to the x, the n minus 1 times h. And then I don't really know what this next coefficient is going to look like without knowing what n is, but it's going to be this coefficient n2 times x to the n minus 2 times h squared. I'm going to skip all the middle terms. I have no idea how many there will be. And then I'll write out the last few. So again, n2 x squared h to the n minus 2 plus n x h to the n minus 1. I need more room, don't I? Plus h to the n minus x to the n. I should pause there because it got really out of control. Any questions about that expansion I just did? Go ahead. So I'll go ahead and collect it in parentheses. So this right here in the parentheses, that is x plus h to the power of it. So I could expand that out. Give me n. I can write out the expansion. I'm trying to generalize this. I have no idea how big ants are. But yeah, I mean, it's very symmetrical. Where can I put it? I'll delete this for now. Like, for example, if I said x plus h to the fourth power, I know that this is going to be x to the fourth plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h cubed. So that's one of the parts of binomial, that binomial expansion theorem, which I'm guessing most of you have seen before, whether or not you remember it. But that expansion, you're going to have, I have my two terms of my binomial. Power on one is going to decrease while the other one increases. The coefficients are going to be symmetrical. 1, 4, 6, 4, 1. They're going to be symmetrical in this general case as well. And really, that symmetry is part of what I'm relying on here. Anything else? Go ahead. Yep. Oh, yeah. Now I agree with myself. Okay. All right. So I expanded. I don't know if you want to say simplified. It definitely doesn't look very simple. But in what I've expanded in that last step there, did anything happen that was good for us in trying to find this limit? There's one big thing that happened. It's kind of subtle. Oh, yeah. So these two things cancel. And remember, and maybe you haven't noticed this, but I'm guessing many of you have, is that when you're trying to use the difference quotient to evaluate these limits, you're trying to get to a place where you can cancel that h in the denominator out of everything in the numerator. Are we there now? Okay. And that canceling out of the x to the power of n with the negative version of that now allows us to do it. So now I have n to the x to the n minus 1 plus n2 to the x to the n minus 2 times h, all the middle terms. So basically everything in the numerator had its power of h decreased by 1. All right, so it still looks pretty gross, right? Can I evaluate this limit now? So what is this limit equal to now? Let's start from the right. What's going to happen to this term? So that goes to 0. How about the next one, the one next to the left? So everything with an h in it is going to go to 0, right? So I'm only left with n times x to the n minus 1. Those of you who've seen the power before, you'll recognize that. So now that we have this, we can use this. I know when I have, x raised to some power, I can just use this thing. Any questions on how I develop this? All right, so now we can take advantage of it. So let's find the derivative of these 4 functions here. I can go back. Take 10 more seconds. If you've got a copy after that, then this will be available shortly after we're done here. I'll put it online. Has anyone ever seen this proof before? One person? All right. So let's take advantage of it now. F of x equals x to the sixth. If that's true, then what does f prime of x equal to? It's x to the fifth. You agree with that? Yep. So I'll just put it up here. F prime of x is equal to nx to the n minus 1 when f of x is equal to x to some power n. How about y prime, this next one? Yep. Bring down the power and then decrease the power by 1. G prime of t. T cubed and h prime of x. Zero. How come? That's oh man, I didn't trap you. So one thing to keep an eye out for, I mean, it's tempting, you see, when you're kind of first getting into the power rule, it's tempting to see, oh, that has a power on it, bring down the power and decrease the power, but yeah, pi is just a constant. Yeah, so let's just talk about g of t versus h of x. In the function g of t, what's the variable I'm taking a derivative with respect to? T. In h of x, what's that variable? Right. So, I mean, if this was x to the 6, that'd be different, but yeah, pi to the 6 is just a number. Anything else on these examples? All right. That is something we'll talk about in a little bit. But maybe we can anticipate it. Let's say, for example, what letter haven't I used? Let's say k of x is equal to 3x to the 6th. What do we think k prime would be? How come? Yeah. Okay. So we're saying, so look at the way f and k are related. I just tripled f, right? So does it make sense that our derivative is simply the triple of the original derivative? So think about that for a bit. We'll talk about that in a few minutes. I'm not gonna spoil it whether or not that's accurate yet. So when I developed the power rule, I said that n had to be a positive integer, but really that power rule works for any value of n. So if I have f of x equals x to the n is any real number. So we could take advantage of that for anything we can, any function we could manipulate to fit that power rule, we can now take a derivative of. So is there a way we could rewrite f of x to make the power rule more apparent? Was that? Negative x squared? Yeah, I think that's what you meant. Yep. So f of x equals x to the negative 2. In that case, what would f prime of x be equal to? Negative 2x to the negative third? We agree with that? Absolutely true. And pretend that I had these variables consistent. Can I rewrite g of x?
Yeah.
As? That's good. We go a little deeper. I guess what I'm after is this. Can I just write this as a single power on x?
Oh,
Go ahead, Thomas. X to the 2/3, yeah. And really, yeah, what I have here in the middle, x squared to the 1/3 power, that's absolutely true. Then you can use your raise a power to a power, just multiply those together. So we have g of x equals x to the 2/3. What does that mean about g prime of x? What is the value of n in this case? 2/3. We agree with this? Okay, I like it. If you'd like to rewrite it, which is not totally crucial, but those things are true. Any questions? Okay. So, got a couple of different things to do here. I want to find the equation of the tangent and the normal lines, which is not something we've talked about yet, but we will right now. So this curve at that point. So, can I use the power rule on this function? If I want to use the power rule, might help us to rewrite that function. How can I re-express it? X to the first times x to the half. Can I combine those? X to 3/2. Very good. Which means f prime of x is equal to what? All right. So let's do the tangent line first. I have the derivative, 3/2 times radical x. I want to find the full equation of a tangent line. So how should I continue? So here's our trying to get an equation that looks like this. So I got y, mx, and b. Is there anything here that I know so far? Okay. I know that y and x are 1. Is there anything else I can figure out? How do I get m? Good. So one other thing I want to do here is this. I want to find f prime of 1, which is equal to 3/2 times the square root of 1, which is 3/2. I think that gives me a value of b of -1/2. So y equals 3/2 x minus 1/2. Any questions on tangent line? So this is the tangent. Has anyone seen that terminology, the normal line, before? So what the normal line is, it is the line that is perpendicular to the tangent line. So perpendicular to tangent lines. If I know that two lines are perpendicular to each other, you remember what that says about their slopes, how they're related to each other? Opposite what? So I hear opposite, I hear inverse, I hear reciprocal. So yeah, so both those things have to happen. So I'll give you a couple ways to look at this. So basically, the slope of the normal line is going to be negative 2/3. So I'll give you another way to think about this here. M1 is perpendicular to M2 if M1 times M2 is equal to -1, which is the same thing as that one is the negative reciprocal of the other. Yep, that's the definition of normal line. It's perpendicular to the curve at that point. So I have its slope now. How do I find the full equation of the line? I know that the point is going to be the same place. I know the slope is negative 2/3. I believe that means B is equal to 5/3. Then I have this equation y equals negative 2/3 x plus 5/3. Go ahead, question? Okay. If the slopes are perpendicular, you can multiply them together, they'll always be -1. Any questions on how I got either one of those equations? All right, and just want to illustrate both. So the red is the curve, f of x equals x 3/2. Blue line is the tangent we found, and the green line is the normal that we found. So a few differentiation rules, or these two we've proved out. We can use those all the time now. These other two I will not prove for you. But we could. I mean, it's something you could do using the difference quotient. So the derivative of any constant is 0. Power rule we've done a lot with in the last few examples. That constant multiple absolutely does work the way that we said it does. If I have some function f and I multiply it by some constant c, that's the same thing as taking the derivative of f and then multiplying that derivative by that same constant. Any questions so far? Yeah, absolutely. And the sum and difference, this is something we'll take advantage of a lot. If you have multiple terms that you can discretely break up because they're added or subtracted, you can just take the derivative of, you can treat them individually. Okay, so I can throw all this stuff at you all at once. But if I want to evaluate that derivative, then I really could say this: it's the derivative of x to the eighth plus 12 times the derivative of x to the fifth This is probably not probably not a detail that I'll use very often or ever again, but this is just highlighting the fact that it's more valuable to think about a derivative like this because looking at it as one complicated function is going to be counterproductive when you could just take it all in individual terms. So what's the derivative of x to the eighth? Yep. And then the derivative of x to the fifth is it will be 60, but I'm going to really go slow for this first one. What's the derivative of x to the fourth? X to the third. Plus 10 times 3x squared minus 6 times. X is a little deceptive. What's the derivative of x? Just 1, right? So I write 1x to 0. And then what's the derivative of 5? 0. So if we simplify everything, 8x to 7 plus 60x to the fourth minus 16x cubed plus 30x squared minus 6. So any questions on combining that the way we did? Okay. That's the lab end here. Absolutely. I mean to do that. You get what you needed? Okay. All right, and we'll finish up on this one. I want to find the point on this curve where the tangent is horizontal. Basically, I want to find where if I were to draw a tangent line to this graph, where would that tangent line be horizontal? The idea is how we can get started there. That's going to be where it switches. So yeah, I got to find those places where it switches. So I don't know what this graph looks like, but let's just draw something to help us. Now I'm looking for these points. So if I'm asking you about tangent lines and slopes of them, what do you think I need to do? Find where the slope is 0, and if I want to find where the slope is 0, how can I do that? What do I need to do? But before I do that, I have to. There you go. That's what I was trying to get at. So I need to find the derivative, right? Which in this case would be what? You agree with that? All right, and I heard somebody else say it. I'm looking for where the tangent is horizontal. So what do I want to do with this derivative? What do I need it to be equal to? 0. Can I solve this equation? What should I do next? I'm gonna do you one better. Like it's gonna get us to the same place, but all right. So I have 4x times x squared minus 3 equals 0, which means I can do this. 4x equals 0. X squared minus 3 equals 0. So what values of x do I have? And negative radical 3. So this is the part you need the derivative to figure out. I want to find all those x values where the tangent is horizontal, but I want to find those points. So let's find the full coordinates. So x is 0, x is radical 3, x is negative radical 3. If I plug in 0, what point should I get? 4? How do you know it's 4 and not 0? What did you plug 0 back into? Put it back into x in the y equation, right? And that's a distinction that I want to make here. There's a difference between the rate of change of the function and the location of points on the function. So, we've said that a function is a function, but the derivative is also a function. So just a word of warning to be careful about. Be careful that you're using the function for the thing they're actually designed to do, the thing they're actually meant for. All right. If I plug in radical 3, what is radical 3 to the 4th power? 9 minus 18 plus 4. 5. Again, negative 5. All right. Any questions on that one? Go ahead. So if I keep working through this one, you get x squared equals 3, right? But there are 2 square roots of 3. Anything else? All right. Last call for quizzes before you walk out. If you got the paper copies, I'm going to post another one sometime tonight. It's going to be quite a bit shorter because I only have you 2 days this week. Then I'll also send out that survey for the review sessions.